Assalamu alaikum warahmatullah. So in the last lecture actually we discussed about different we discussed about the random processes, okay, and we have seen there are different two types of random processes, continuous and discrete, and we have seen some important characterization of random processes like the mean, autocorrelation function, autocovariance functions, etc. Okay, now we will see today some two different class of random processes, that is known as the stationary random process. One important class of random process which is known as the stationary random process. Okay, stationary random process. Okay, so a random process, you know, it will be something like you can represent like this. Let's say this is some random process and it is a function of time. Let's say this is x of t. So when do we say it is stationary? Let us assume that let us consider some points. Let's say this is a point at t1, let's say this is a t2, and this is t3, then t4, t5, and so on. Okay, now we will consider, so what is the joint distribution of the variable? Suppose at t1 you have a random variable, let's say x1, you have something like it takes the value x2 and it takes the value at this point as x3. So there is, we can define some joint distribution for this that we have seen in the last lecture. So the joint distribution is fx, okay, of t1, okay, and x t1 fx t2 and so on. Suppose we take up to some k points, let's say tk. So at tk, which takes the values like x1, x2, x3 and so on up to xk. This is the joint distribution. Now we will observe at some other particular time, which is here, for example, that means this time you can represent like t1 plus tau. Okay, now we will consider another time here, so this time you can consider like t2 plus tau. Similarly, you can consider this time, so this time you can consider it here it as t3 plus tau and so on. That means you are observing at t1 and you are taking a corresponding time t1 plus tau. Similarly, for corresponding to t2, you are just delaying by the same amount, okay, t2 plus tau and so on. That means you have tk, for tk you have tk plus tau. That means you are assigning a delay for this, okay, you are observing after a particular delay. Then what will be the distribution? If this distribution is same as whatever distribution you have obtained at t1, t2 and tk, if you are getting the same distribution, so the distribution at this point you have some distribution, and at this points after a constant delay you have a distribution. Okay, if both these distributions are same, then we will say that the random process is strictly stationary. So how we can write it? So it is nothing but fx of t1 plus tau, fx of t2 plus tau and so on up to x of tk plus tau, okay, which takes the value same thing x1, x2 up to xk. So if these both distributions are same, then we will say that the random process is strictly stationary. Then the random process is strictly stationary. So what does it mean? Why we are calling stationary even though the random process is changing with respect to time? It is strictly stationary. That means that the characteristics of the random variable, the characteristics, what are the characteristics? The statistical characteristics we can say. That means the statistical characteristics of the random variables, the statistical characteristics of the random variables are not changing. That's why we are getting same distribution, not changing with respect to time. Okay, that means that's why we are getting the same distribution. So same distribution means the properties, that means the characteristics of the random variables are not changing with respect to time. Then we will call the random process as strictly stationary random process. I hope this concept is very clear to you. Now, but this kind of processes are rare anyway. But so for easy to handle, so for making easy to handle, we have practically some other process, let us which is known as the wide sense stationary process. So wide sense stationary, it is not strictly stationary, but in a wide sense we can say this process is okay, this is stationary process, stationary. Okay, so what is this wide sense stationary? So if we take the first order distribution, what is first order distribution? We will just observe only at time t, okay, and we have the distribution fx of x of t, fx of t of x. Then if it follows the same distribution at t plus tau, which takes the value small x, and all this we can say that it is not depending upon the time, since you see here whatever time you observe, it is not depending upon the delay. So we can say that it is nothing but fx of x. So if the process is having this kind of property, with that means the first order distribution is independent of time. Okay, the first order distribution is independent of time. You can not see any time axis, there is no time notion here, because the distribution is not changing with the time. Okay, the distribution is not changing with the time. That means that the first order distribution means we can say that the mean of the random variable, the mean of the random processes which is describing the random variable, the mean is not depending on time. We can say the mean is not depending on time. That means mu x at a particular time will be same for all the time. That means mu x will not be a function of time. You can see here the mean of the random variable is always constant. So whatever time you observe, suppose you observe here, so you observe at particular time t1, you observe at particular time t2, whatever average value you are getting mu x of t1, and here you are getting mu x of t2, all this will be same if you observe at any time, and it will be equal to mu x, just mu x, because it will not depend upon the function of time. Okay, so this is the x of t and this is time. So this is one of the property of wide sense stationary process. We will call it as WSS. Okay, wide sense stationary random process. Now there is one more property, the second order distribution. That means the second property is that the second order distribution fx at t1 you will observe, at t2 also you will observe, and you will get a value x1 and x2, and this distribution will be same as you observe at 0, for example, you observe at 0 and you observe at t2 minus t1. That means if you are observing at t1 and t2, then t2 minus t1, suppose this is equal to tau, it is only the time difference. Okay, time difference. And here also you are observing here and observing at t2 minus t1. That means the time difference is t2 minus t1 minus 0. Again you are getting t2 minus t1. Let us say this is equal to tau. Again it is the time difference. Okay, so it will be different depending only on the time difference. Okay, that means for example this is x1 and x2. Okay, so it is depending only on the time difference. That means it is independent. The second order distribution, we can say the second order distribution is independent of time. Okay, but it depends only on the time difference. Okay, sorry, difference. That means suppose you have something like fx of t1 and t2, which takes the value x1 and x2. This will be same. Suppose t2 minus t1 is equal to tau. This will be same as fx of t3 and fx of t4, which takes the value x1 and x2, and it is given that t4 minus t3 is also tau. If both are same, this difference is same, it is independent upon the time that you are observing, but it will depend only on the time difference, how much difference is there. That means you have a random process x of t, which is something like this. Okay, this is time. So you will observe at t1 and t2, and you observe at another time t3 and t4. Suppose this difference is tau, this difference is tau, then the second order distribution will be same for both. Second order distribution function will be same for t1 t2 pair and t3 t4 pair, if both are having the differences same. Okay, this difference and this difference both are same. Okay, that's what the that means that is not a second order distribution. So what do you mean by this? The second order distribution means you are talking about the time difference, means you are talking about the autocorrelation function. So the autocorrelation function, that means Rx of t comma tau is not depending upon the time. That not depending upon time means not depending on time means that, okay, not here, means that it will be equal to Rx of time. So that Rx of tau, that means it is not depending on time, it is, this is only the time difference. Okay, suppose if you take Rx of t1 and t2, that will be same as Rx of t3 and t4 if t4 minus t3 is equal to t2 minus t1. If both are same, then it will be having the same autocorrelation function, it will not be changing. So that is the property. So we will see some examples anyway. So before that we will, before seeing a problem, we will see some properties of autocorrelation function for the Whiteson stationary process. Okay. So the properties, so these are two properties we have seen now, this by definition. So these are the two properties. So Whiteson stationary means that it has two properties, property 1 and property 2. Property 1 means that the mean does not change with time, and the second property is that the autocorrelation function does not change with time. The ACF will not change with respect to time. Okay, these are the two properties. So this is one property and this is another property. Okay, I will put it in the box, that's better. Okay, so this is another property. So that's what we are explaining mathematically. Okay, now we will see some properties of autocorrelation function for Whiteson stationary random processes. Okay, and you know that the autocorrelation function Rx of t1 and t2, I told you it is nothing but expected value of x of t1 into x of t2. This we have already seen. This will be written as, if you observe at time t, then you just need to see another time t plus tau. Okay, this will be same as, everything will be equal. If you observe at time t, you can consider the previous time also, there is no issue, because it is depending only upon the time difference. It is nothing but Rx of tau. Okay, for Whiteson, it is not a function of time. So it is depending only on time difference. That's what the meaning. Okay, it is depending only on the time difference. Okay, that means Rx of t comma tau, okay, will be equal to Rx of tau. So you observe at any time, there is no issue. Okay, t comma tau means you will take expected value of x of t and x of t and x of t plus tau, that's it. So it will be depending only on the time difference, not the particular time difference. Okay, now we will see some more things. So Rx of tau you can write like this: Rx of tau is nothing but expected value of x of t into x of t plus tau. Okay, now let at tau equal to 0 we will get the expect Rx of 0. Rx of 0 is nothing but expected value of x of t into x of t plus 0, right? This is nothing but expected value of x of t the whole square. What is this? You know that this is the mean square value. Mean square value, that means the average power of the signal. So if you know the autocorrelation function, you can find the average power of the random signal. Okay, now so this is one of the property. Now the second property is we will talk about the properties. I will put the heading properties. So the second property is nothing but Rx of tau will be same as Rx of minus tau. So it is an even function, that means it is an even function. So it will be having a structure like this, maybe something like this. So if you take something like tau here, the value will be same for minus tau also. Okay, sometimes you can get a graph like this. Okay, so if you take here some tau 1, then it will be having some same value at minus tau 1 also. So how we can prove it? You know that Rx of tau, we have Rx of tau is equal to the expected value of x of t into x of t plus tau, and Rx of minus tau is equal to expected value of x of t and x of t minus tau. Okay, now what is the time difference here? Time difference is equal to tau, and here also the time difference again is nothing but tau, because you see here the time difference is t minus tau, this is equal to tau, and here the time difference is t plus tau minus t, which is equal to tau. So both time difference are same, so Rx of tau will be equal to Rx of minus tau in the case of in the case of wide sense stationary process, WSS. Okay, and I told you, and also the third property, I think this is the second property, yeah, the third property is that the Rx of 0, that means if you are observing at the same time, that means the average power Rx of 0 will be always greater than or equal to Rx of tau for all tau. Okay, that means you will be getting a graph something like this. So the maximum will be obtaining only, this is Rx of 0. So usually the maximum will be appearing at Rx of 0. So that's what the that's what the property of the autocorrelation function for the wide sense stationary process. Now we will see a problem example. So let x of t is given as cosine of omega t plus theta. Okay, and this theta is a uniformly distributed random variable. It is a uniformly distributed random variable in the interval minus pi to pi. Okay, now you have to obtain the mean of the random process and the autocorrelation. Okay, mean you have to find the mean, autocorrelation function, and the auto covariance function, autocovariance, sorry. Okay, autocorrelation and autocovariance. So we will solve this problem. It is given that x of t is equal to cosine of omega t plus theta, and here theta is the random variable. So what is the mean of the random variable? Mu x of t is nothing but the expected value of x of t. Okay, so this is nothing but expected value of cosine, okay, omega t plus theta, and you will be getting here, that's it. Okay, so you will be getting here 1 by 2 pi, okay, because expected value you have okay, you have to first find the probability density function. So the probability density function is 1 by pi minus pi. Okay, so this is nothing but 1 by 2 pi. So it is a uniformly distributed between pi and minus phi. So this amplitude will be equal, to 1 by 2 pi. Okay, so we have to integrate from minus pi to pi. 1 by 2 pi is the probability density function, and our random process is cosine of omega t plus theta. Okay, and we have to integrate with respect to d theta. So this is nothing but 1 by 2 pi integral minus pi to pi cosine of omega t with respect to theta and d theta. If you take if you integrate this with respect to theta, you can see that this will be equal to 0. Okay, so the average value is 0, and you know that the average value is 0 now. Okay, now you know that we have to find the autocorrelation function. And what is the relation between the autocorrelation function? Autocorrelation function, you know, it is Rx of t comma tau, and the autocovariance function is Rx of t comma tau minus mu x of t into mu x of t plus tau. Okay, t plus tau. So that's what the t plus tau, or okay, you can in another way also you can write it, all are same anyway. Rx of t1 t2, observe at 2 times t1 and t2, that means t2 minus t1 is equal to tau, and the autocovariance function is nothing but cx of t1 and t2, which is equal to Rx of t1 into Rx of t1 t2 minus mu x of t1 into mu x of t2. But you know that these guys both are zeros, so this part is 0. So in our case Rx of t1 and t2 both are same as Cx of t1 and t2. Okay, both are same because the average value is 0. Now we will see what is Rx of t1 t2. Okay, it is nothing but the expected value of x of t1 into x of t2, right? This is equal to the expected value of cosine of omega t 1 plus theta into cosine of omega t2 plus theta. Okay, that's it. Okay, I will write it in another line, multiplied with cosine of omega t2 plus theta. Okay, that's it. Now you have to use trigonometric identities. So you know that how to find expectation. It is 1 by 2 pi, and you have to integrate from minus pi to pi, then cosine of omega t1 plus theta into cosine of omega t2 plus theta, and you have to integrate with respect to d theta. But you know that cosine of a into cosine of b, okay, I am going to use this formula for that. So that cosine of a into cosine of b, I am using this formula. Cosine of this is like in the cosine of a, and this is the cosine of b. So you can check the trigonometric identities. Then after simplification you will get it as integral minus pi to pi 1 by 2 pi. This is nothing but the PDF into cosine of, there is an half also will come, half cosine of omega into t1 minus t2, okay, in plus cosine of omega t1 plus t2, okay. Then you will get one more thing, plus 2 theta, okay, that's it, into d theta. But you know that this guy, when you integrate with respect to it, contains 2 theta. So if you integrate this part, if you integrate this part with respect to theta, it will become 0, as in our previous case. If there is a term theta, you see here our integration has gone to 0, okay, 0. So like this, if you have a term theta, you can try the integration, then you will get it as 0. So what you will get here, it is nothing but 1 by 2 pi integral minus pi to pi, okay, half of cosine of omega t1 minus t2. The second integral become 0, okay, if you integrate it. So this become, and you know this is, so you know this is d theta, there is no term theta here, so the integration will be 1 by 2 into, this is 1 by 2 pi into cosine of omega t1 minus t2, this is a constant, integral d theta from minus pi to pi, okay. So this you will get it as, this term you will get it as 2 pi, so that the answer become this 2 pi here, you will get it as 2 pi, and there is a 2 pi here, so this will cancel. So finally you will be getting half of cosine of omega into t1 minus t2, okay. That means the Rx of t1 t2, you will get it as half cosine of omega into t1 minus t2. Let us assume that t1 minus t2 is equal to some tau, then Rx of tau, you will get it as half of cosine of omega tau. So the autocorrelation function will be looking like this, okay. So it is also it is satisfying all the properties also. So this is, sorry, not t, it is the function of tau, so Rx of tau, okay, and this part is half, maximum is half, okay. So I hope this is clear to you. Now we will see some important properties, how to find the, okay, we will see what are the important okay, properties of the autocorrelation function, that I think we have already seen it. Now we will see one more, okay, we have seen the problem also. Now we will see another thing which is known as the ergodic process, okay, another kind of random process which is known as the ergodic process. Ergodic process, ergodic process. So ergodic process means the time average of the process, time average will be equal to the ensemble average. Suppose you have a random process, okay, this is x of t and this is time axis. Then the ergodic process means, suppose you are observing at particular time instant, so this will be applicable only if applicable only if the process is stationary, okay. If the process is stationary, then only it is applicable. That means the statistical characteristics of the process should not change with time. So we are talking about the ergodic process now. So what do you mean by this? Suppose you are observing at a particular time instant, let's say t1, okay, and you know the distribution, then this you are getting a value x1, then the distribution, let's say you consider t, and the distribution it fx of t, and from this distribution actually you can find the PDF fx of x of t of x, and if you know the PDF, you can find what is the random what is the expected value of this x of t, okay, at particular time instant t that we have considered here, okay, then you will get the mu x of t. But I told you the ergodic process that is applicable only for the stationary process, then it will be a constant mu x, okay. So this averaging process, actually we are using the distribution, so this averaging process, this averaging process where which we use the PDF is known as the ensemble, it is known as the ensemble average, okay, this is the ensemble average. Now you can take the average in another way also, the same process. I will try to repeat the same anyway, please, okay, same x of t, okay. I am going to find the average. How I can find the average? I will integrate the x of t, that means I will add all these x of t's with respect to t, and I am going to consider the time span. For example, the time span is starting from minus t, okay, this, so this is my random process. I am considering some time span minus t to t, so I am going to integrate from minus t to t, add all these things, and what is the width of this? It is nothing but 2t, so I am going to divide it by 2t, okay. Then I will be getting an average. This is the average of this signal, and this is known as the time average, okay, because we have integrated with respect to time and find the average. So this is known as the time average. So this average we will call as the time average, okay, mu x of t, okay. Now this mu x of t, the mu x of t is for example, the mu x of, this is known as mu x of t, and previously we have called it as mu x, okay. This is the ensemble average. So if both these averages, that means if both are equal, if the time average mu x of t, and you should note that this t is a very large number, t is tending to infinity anyway, okay. So the t is a very large number. So if the time average mu x of t is equal to the ensemble average mu x, okay, then our process is ergodic process, is said to be ergodic, is said to be ergodic. So ergodic means the time average will be equal to the statistical average, okay. So if you take that statistical average, then the time average will be equal to the statistical average. Now I can say that for the ergodic process, the following definitions hold. Limit t tends to infinity, mu x of t will be equal to some mu x, okay. That means the time average, if you take the average over time, it will be equal to the statistical average. How you are getting statistical average? The statistical average is obtained by using the PDF. You have to integrate and find it out, okay. So the time average, so this integrating, finding out the PDF and integrating it, it is a difficult task. So instead, if you know the process is ergodic, it is very easy to handle it, because you just need to observe the process for a long time and then you just take the average. That's what we have seen in our MATLAB class, okay. So the time average is equal to the ensemble average, That's it. Okay, time average is equal to. Now limit, the second property, limits t tends to infinity, the variance of mu x of t, that is equal to 0. That means this will be a constant, this will tends to a constant, it will not change, it will tend to a constant, tends to a constant. That means the mean will tend to a constant as t tends to infinity. Okay, that means if something become constant, the variance of a constant, you have already seen, the variance of a constant is 0. That's why. So that's it. Now the third property is nothing but Rx of tau, which is averaged over t, it is nothing but 1 by 2t. Okay, that is not autocorrelation function. You are finding the autocorrelation function, x of t plus tau into x of t into dt. This will be same as that of the Rx of tau. That means this is the ensemble average and this is the time average. Okay, both will be same. That means limit t tends to infinity, the variance of this Rx of tau comma t, that means it will tend to a constant number. That means it will be a constant number or it will be a constant function, not a constant function anyway. It will be depending, it will not be depending upon anything else, it will not be a function of time or anything else. So then it will be a constant, we can say in that sense. Okay, okay, it will be, then the variance will be equal to 0. Okay, so these are all the properties of the ergodic process. So I hope you understood the concept of ergodic process, and these are all the notions which are very, very important for the communication engineers. Okay, now we will see another important topic which is known as the power spectral density. Okay, power spectral density, power spectral density. So if you know the autocorrelation function, if you know the autocorrelation function which is defined as Rx of tau, okay, we are talking about the wide sense stationary process, Rx of tau, then the power spectral density is defined as, because the power, this is showing actually the power. So if you take the Fourier transform of this, is showing the power variation anyway with respect to tau, with respect to tau. So if you take the Fourier transform, you will get how the power is distributed in frequency. So this is known as the power spectral density, PSD. Okay, PSD, power spectral density, is nothing but the Fourier transform of the autocorrelation function. That means the Fourier transform of Rx of tau. So how to find the Fourier transform? You know this, it is nothing but integral minus infinity to infinity Rx of tau into e power minus j 2 pi f. This is a function of tau, so I have to use tau here, d tau. Okay, so this is nothing but xx of f. So this is how you can find the power spectral density. This is tau. Okay, now how to find the autocorrelation function from the power spectral density? Just need to take the inverse Fourier transform, minus infinity to infinity xx of f e power j 2 pi f into tau df. Okay, so this is the autocorrelation function. Okay, this autocorrelation function is equal to inverse Fourier transform of Rx of tau. That means the inverse Fourier transform of the power spectral density, power spectral density. Okay, I hope this is clear to you. Now there are some properties for this. So property 1, that means xx of 0 is nothing but, you have to put f is equal to 0, put f equal to 0. So this is nothing but integral minus infinity to infinity Rx of tau into e power minus j 2 pi f into tau d tau, but I am going to put f equal to 0, then it become e power j 0, then it become minus infinity to infinity Rx of tau into d tau. This is nothing but the area under Rx of tau. So xx of 0 is nothing but the area under Rx of tau. And what is the unit of this xx of f? That I forgot to tell you. The unit of xx of f, what is it? It is nothing but watts per hertz. That means how much power is distributed per frequency. That means in one unit frequency, you can say. So if you take the area under the power spectral density, you will get the total power of the signal. And you know that the second property, okay, so you know that what will be the area under. Now the area under xx of f, that means area under power spectral density, is nothing but integral minus infinity to infinity xx of f df is nothing but the power of the signal, or the average power of the signal, and it is nothing but Rx of 0. Okay, so there is some interesting relationship between this. So if you want to find the total power of the signal, you just need to take the area under the power spectral density. Next property is property 2. Next property, the expected value of x square of t is nothing but Rx of 0. Okay, it is nothing but the area under, that's what we have discussed now. So df, so the average power, so it is considered as the second property. The average power we have just discussed now, this one. Okay, this is the second property, actually this is the property 2. So we are going to define this. So average power of the signal. Okay, so you see here, this is hertz and this unit is watts per hertz. So the total power, you will get it as power in watts. Okay, now property 3, xx of f will be always greater than or equal to 0. It is for all f, because the power is always a positive quantity, because this is nothing but watts per hertz power spectral density. So it will be for greater than 0 for all f. Okay, this is the third property. Next property 4, xx of minus f is equal to xs of f. It is because it is an even function, and also you know that Rx of tau is also equal to Rx of minus tau. Okay, so these are all the properties. And one more thing, if you know the power spectral density, you can easily find the PDF of the in frequency domain as follows. Property 5, the px, that is the probability density function, can be found out by, if you know xx of f, then you have to just normalize it. So this is the process of normalization. Normalization means the area under become 1 now. So we will just divide it by the total area under it, xx of f df. So if you do like this, the total area, so then if you do like this, then integral px of f df from minus infinity to infinity, this will become 1. It is because of this. Okay, now this is the another property. Now we will see a problem how to find the power spectral density if you know the autocorrelation function. So the example, you have seen x of t as a random process, a into, let's say you have a random process cosine of 2 pi f into t, okay, fc into t plus theta, you have seen, and theta is a uniform distributed random variable between minus pi to pi. Then you have seen that the autocorrelation function was for this problem. I am saying we have seen a problem just recently. We have seen a problem. Yes, this problem I am saying. Okay, this is omega. Instead of omega, it is nothing but 2 pi f fc. Okay, omega. So this is 2 pi f is nothing but omega. Okay, now we have got the autocorrelation function as cosine of 2 pi f c, okay, into tau. If there is a, we got it as 1 by 2, but if there is a here, then it will become a by 2, right? Am I correct? Yes. So this is the autocorrelation function. So look the previous problem for getting this. We have already solved this. Okay. Now what will be? Now we are going to find the power spectral density. Okay, that is xx of f. That means xx of f is nothing but I think I have made a mistake here. It will be a square. Okay, it will be a square because x of t1 into x of t2. That means a into a it will come, so a square. So what is so it is nothing but the Fourier transform of a square by 2 into cosine of 2 pi fc into tau. Okay, then what is the Fourier transform of this? You know that the Fourier transform of this is nothing but a square by 4. I hope that you have studied from course 702. So the a square by 4 into delta of f minus fc plus delta of f plus fc. Okay, so this is the Fourier transform. So I will write it again. Xx of f become a square by 4 into delta of f minus fc plus delta of f plus fc. Okay, now we can plot it. This is the frequency axis. Okay, and xx of f will be here and the unit is watts per hertz. Okay, now you are getting two impulses, one at delta of f minus fc. So this is at this is delta of f minus fc, but the amplitude is a square by 4, and there is this is at fc, and there is another impulse which is a square by 4 into delta of f plus delta of f plus fc. Okay, so this is nothing but the power spectral density. Now if you want to find the average power of the signal, the power, you know that the power is nothing but Rx of tau at tau equal to 0. That means Rx of 0, it is nothing but a square by 2 into 1, which is nothing but a square by 2. Okay, this is the power of the signal. Now that is by using autocorrelation function. Now using the power spectral density, you just integrate it. So if you integrate the first term, integrate this term, if you integrate this, what you will get, it is nothing but area under the delta impulse function will be 1, so it will be a square by 4. Then there is nothing in this space here, nothing here. Now you have another term. Okay, so integrate it. So plus integrate it, integrate, it will be a square by 4. So the total will be a square by 4 plus a square by 4 is nothing but a square by 2. So you are getting the same power. Okay, if you are using the autocorrelation function or the power spectral density. So the area under power spectral density, so the important points to remember, points is nothing but Rx of, sorry, the power spectral density is nothing but, it is nothing but the Fourier transform of the autocorrelation function. Okay, and the unit is watts per hertz. Okay, and Rx of 0 is nothing but the power of the signal or the average power of signal. The area under the power spectral density, that means the area under power spectral density will be equal to the power of the signal, that means the average power of the signal. Average power of signal, and it is nothing but Rx of 0. Okay. So, these are all the important points to remember. Okay. Points to remember. Okay. I hope everything is clear to you. Thank you.